All right, guys, can you hear me?
Yes.
All right, great. Today, let's start a new section. So today we'll introduce two concepts. So the first one is called the least. Oh, just a moment, let me. All right. All right, so the first concept in this class is called the least common multiples. Right, so we learned the concept multiples last time, right? So basically that means, so A is a multiple of B if A equals B times an integer, right? So here we'll talk about a common multiple. So that means we are not only consider a multiple of a single number. Instead, in this time, we'll consider a multiple of like two or more numbers, right? So for example, so first let's look at the definitions. So whenever we discuss the common multiples, so there are at least two numbers, A and B, right? So they are positive integers. So if A is a multiple, so if a number is a multiple of both A and B, then we say the number is a common multiple of A and B. The smallest such number is called the least common multiple, right? So, and it has a special notation. It's just a LCM bracket A and B. So let's look at the next example, the problem 30.25. So A, list all the 5 least positive multiples of 18. So this is easy, right? So the smallest multiple of 18 will be 18 itself, right? Because that equals to 18 times 1. Then the next one will be 36. Then the next one is 54. And the next one is 72. And the last one is 90. Right? So basically, you just multiply 18 by 1, 2, 3, 4, 5, respectively. And then, so let's look at the question B. So list the 5 smallest positive integer, positive multiple of 24. So basically, we'll do the same thing, right? So they are 24, so 48, 72, 96, and 120. Right? So again, you can just multiply 24 by 1, 2, 3, 4, 5, respectively, to get the 5 numbers. Well, so let's look at the question C. So list the 3 smallest positive multiples of 18 and 24. So from the two lists, can you find any like common factor or say the common multiples? Do you see any common multiples in the two lists? So any repeated number there?
72 and 72.
Good. So I'm sorry, what did you say?
I said they both have 72.
Yes, they both have 72, right? So in this case, we can say, well, so 72 is a common multiple of 18 and 24, right? So by the way, is 72 the smallest one? Is 72 the least common multiple of 18 and 24? So I'm asking the question D. Is 72 the LCM of 18 and 24. So, or say, so from the two lists, do you see any other, or say, do you see any smaller common multiples?
No.
No, right? Because 72 is the smallest one. So that means 72 is the LCM of 18 and 24. Right? Yes. And then, so let's go back to the question C. So list the three smallest positive multiples of both 18 and 24. So now you have known that 72 is the smallest one. So can you list the next two common multiples? So any ideas? All right, go ahead.
We can just write a few, like a list of the multiples of 18 and 24, and then find the ones that appear in both that are also the smallest.
So we have found the smallest, right? So we are looking for another two. The list, the smallest, I mean the second one and the third one, right? So you're saying that we can list more, like for example, for the multiples of 18s, the next one will be 108, then 126, then 144, and then 162, and the 180, and so on. So for 24, the next one is 144, then 168, 192, and so on. Right? So you can see that we have found the next one, right? So 144 is in both of the list. Right? So, all right, so 72 will be the first one, and the 144 will be the next one. Then can you guess the next one without listing them? Jacob, do you have any idea?
216.
What is that? 200 and 200 and what?
16.
16. All right, so how did you get that?
144%.
Oh, good. That's very good. So actually, so if you look at the three numbers, so you can see that, so 72 is the least common multiples. Actually, 144 is 2 times the LCM. So the next one will be 3 times the LCM, which is 3 times 72, which is 116. Great. So actually, if you're looking for the common multiples, it must be a multiple of the LCM. So here, let me write down the observation. So any common multiples or say of so it must be a multiple of LCM of the two numbers. Right? So just like what you have seen, so all of 72, 144, and 216 are multiples of 72. Okay. All right, so let's look at the next one. So find, there's a typo. So find the prime factorization of the 5 smallest positive multiples of 18. So compare these prime factorizations to the prime factorization of 18. Then do you notice anything interesting? So, well, so we have listed the 5 smallest multiples of 18, right? So they are 18, 36, 54, 72, and 90. And we know that 18 equals 2 times 3 squared, right? So that's the prime factorization of 18. Then can you tell me the prime factorization of 36? Can anyone do that? Oh, Davey?
Isn't it just, can't we just do 2 to the power of 2 times 3 to the power of 2?
Yes, that's correct. So that will be 2 squared times 3 squared. How about 54? Oh, David, can you continue to do the 54?
Don't we just like add another power of 2?
You mean 54 or 36?
For 54. Like since 36 is already 2 to the power of 2 times 3 to the power of 2, doesn't 3 to the power, wait.
Is it? It's not, right?
No.
So can you factor it?
54 goes into 2 and 27.
So 27 equals, so 27 is a power of 3, right? So what is that?
Yeah. Then it equals to 3 to the power of 3.
Very good. So that's 2 times 3 cubed. Then let me write down 72. Oh, so anyone wants to do 72 and 90? Okay. William.
The power is like 2 times, it's 2, no, 2 times,
So what's the exponent for 2?
It's 2 to the power of 4 times 3, times 3 squared.
Are you sure?
Oh no, 2 cubed.
Good. So that's 2 cubed. Great. So how about 90?
90.
Oh. So William, can you continue to do 90?
Okay. It's 2 times 3 to the 2 times 3 2 times 3 squared times 5.
All right, so that's the prime factorization of 90. Very good. Then do you see anything interesting? Like, can you summarize something from the five factorizations?
They all have 2 times 3. No, yeah, they all have 2 and 3.
Yeah, that's good. Anything else? So it's not only 2 times 3, right?
Oh, 3 square.
Very good. So actually they have a common factor, which is 2 times 3 squared. And 2 times 3 squared is exactly 18. So you can see that the prime factorization of 36. So this is the prime factorization times 2, right? So where 2 is from, so because 36 equals 18 times 2, right? So that means you only need to multiply the prime factorization of 18 by 2, right? So actually, when you're looking for the prime factorization of 54, you just need to multiply this one by another 3, right? So for 72, just multiply it by another 4, but 4 is 2 squared. So that's 2 cubed times 3 squared. And for 90, you just multiply another 5 there, right? So that's why there is an additional term. All right. So you can see that if A is a multiple of B, then the prime factorization of B must be a part of the prime factorization of A. So let me write it here. So if A is a multiple of B, then the prime factorization of B must be a part right? So if A is a multiple of B, then the prime factorization of B must be a part of the prime factorization of A. Actually, this is a very useful conclusion. So let's see how we use it in the following questions. So let's look at the problem 3.27. The prime factorization of 72 is 2 cubed times 3 squared. Use the given one to determine if the number is a multiple of 72. So definitely you can just divide all of those numbers by 72 and to check it, right? But if we have the prime factorizations, so we have another, or say we have an easier way to do that. So you see 72 equals 2 cubed times 3 squared. Then is this product a part of 2 to the 5th times 3 cubed? So does this product contains everything of the prime factorization of 72? Yes, right? Because it has 2 cubed and also it has 3 squared. Right? So that means 862 is a multiple of 72. Then let's see the second one. So 108 equals 2 to the 4th times 3 squared times 7. How about this? Is that a multiple of 72?
No,
Why not?
because 3 to the power of 2 does not contain 3 to the power of 3. I mean it is. I mean it is.
It is, right?
Yeah, it is, because 2 to the power of 4 contains 2 to the power of 3.
Yeah.
And the 7 is just custom.
Yep, that's good. So we can see that, so the 2 cube is a part of 2 to the 4th, and 3 cube is a part of, 3 square is a part of 3 square itself. And we don't care about any additional term. Okay? So you only to make sure that, so this factorization contains more terms. Right? So that works. So that means 1008 is a multiple of 72. How about 400, whose factorization is 2 to the 4th times 5 squared? Is that a multiple of 72? So does this factorization have 2 cubed and 3 squared? So does it have 2 cubed? Or say, does it contain 2 cubed? Yes, right. So because there is a 2 to the 4th. But how about 3 squared? So you can see it doesn't have anything about 3, right? So this is not a multiple of 72. All right, so let's look at the last one. So the last one is 2 squared times 3 to the 6th. So is that a multiple of 72?
No,
No. Okay, Jacob, why not?
because is 2 squared is less than 2 cubed.
Oh, good. Because so it only has a 2 squared, right? So it's smaller than 2 cubed. So that means it's not a part of the factorization of 2916. So this number is not a multiple of 72. All right, good. Then let's look at the next problem. So how can we use the prime factorization of 24 and 90 to find the least common multiple of the two numbers? All right, so this is a very important technique. So because we're looking for this number as a multiple of both of the two numbers, right? So if you consider their prime factorizations, so 24 equals 2 cubed times 3, and 90 equals 2 times 3 squared times 5. So because the LCM is a multiple of both of them, so the LCM, so let's call it A. So if you consider the prime factorization of A, it must contain both of the factorizations of the two numbers. So right, and here you have to make sure that because A is the least one, which means that's the smallest one, right? So that means we don't need any additional number in the prime factorization. We only need the smallest one. All right, so let's see. So what do we need in the prime factorization of A? So how many 2's do we need? So see that there is a 2 cubed in 24, and there is only a 2 in 90. So how many 2? So what is the exponent, or say what kind of power of 2 do we need? So anyone wants to answer?
Well, the
Okay,
factorizations
Genova. Oh,
prime factorization is basically like you look at the numbers that are like the same, well, like have the same base, and then you look at the ones which are bigger. So then you just, so for 2 cubed times 3, that's 1, and the 2 times 3 squared times 5 is 1. So then 2 cubed and 2 are like the same base, but then 2 cubed is bigger, so then you do 2 cubed, and then there is 3 and 3 squared, and 3 squared is bigger, so it's times 3 squared, and then there is no 5, but then there's only 1 5 on the right, so then times 5, which equals 8 times 9 times 5, which equals 40 times 9, because 8 times 5 and then times 9. So then it's 4 times 9 equals 36, and then put a 0 behind it.
all right, very good. So basically this is the process to find the least common multiple of the two numbers, right? So the first step is to consider the prime factorizations of the two numbers. And then, so the second step, so just like what Genova did, so we need to compare the two prime factorizations. And for each kind of power, we need to pick the larger one. So the second step is to determine the power for each prime number. Right. So for some if a prime number in the factorization of A but not in B, then you can just copy that. Right? But if there's a power in both of the factorizations, you have to pick the larger one. And then, so this is how we find the prime factorization of the LCM. And the last step will be, so eventually you can just find the LCM by multiplying them together. Right. So once you have the factorization, you can easily multiply them together to find the number. Right, so this is the process to find the number. Then let's do one practice. So let's find the 4 LCMs. Right. So in the next problem, there are 4 questions. So can anyone find the LCM of 96 and 144? So let me factor them. 96 equals 2 to the 5th times 3. And 144, what is 144? So that's 2 to the 4th times 3 squared. All right, so can anyone find the LCM of the two numbers? Just tell me the prime factorization of the LCM. So any ideas? All right, so you see that in both of the factorizations, there is a power of 2 and the power of 3. Right? And then, so we just pick the larger one. So for the power of 2, we just take 2 to the 5th. And for the power of 3, we just pick 3 squared. Right? So that will be the prime factorization of the LCM. And then you can just multiply them together by yourself. All right, so then let's look at the second one. So in this case, so their prime factorizations are given. So can you find the prime factorization of the LCM? Can anyone do that?
No.
So anyone wants to do it?
Isn't it just 32 times 9?
Oh, which one? The second one?
No, 2 to the power of 5 times 3 to the power of 2.
Oh, I'm not sure. So you can just calculate it by yourself. Yeah, I think that's 32 times 9. So that's
288.
Oh, no. All right, so that's 288. All right, thank you. Then can you do the second one? So can you calculate the least common multiple of those two numbers? So in this case, the two prime factorizations are given. And you just need to find the prime factorization of the LCM.
$980.
So how did you find that?
I broke down. I broke down the 2835 into 2, 2, 2, 2, and 7. Then I broke down 35 to 5 and 7. Then I did 7 to the power 2 times 2 to the power 2 times 5.
Oh, which one are you talking about?
B.
Oh, B. So in this case, we have the two prime factorizations, right? All right, so let me do it. So you can see that only the first factorization has the power of 2. Right? So we just copy that. And then, so both of them have the power of 3. And we just pick the larger one, which is 3 cubed. And then both of them have the power of 5. So again, we pick the larger one, which is 5 squared. And only the second one has the power of 7. So we just copy that, which is 7 to the first. Okay. So this is the prime factorization of the two numbers. And then you can just multiply them together. I guess that's 100 times 27 times 7. Okay. So basically you just multiply 7 and 27 together. Oh, that's 189.
Hi.
Yep. So the answer will be 18900. All right, so let's do the next one. So if you know that 28 equals 2 squared times 7 and 35 equals 5 times 7, so can you find their LCM?
Or 980.
It's what?
980.
980?
140.
I think I agree with the second one. So I think 140 is the correct answer. So Andrew, can you tell me how you calculate that?
Okay, so first we find the bigger, wait.
Oh.
So first we find the bigger integers, 5, 7, and 2 squared. So 2 squared is 4, so 4 times 5 times 7 is 140.
All right, great. So basically the prime factorization of LCM is 2 squared times 5 times 7. Right? So because, so 2 squared is from the first one, and because 7, so both of them have the power of 7, so we just pick the larger one, and 5 is from the second one. Right? So eventually the answer is 140. All right, so can anyone find the LCM of the three numbers? Actually, it's nothing different. So we can do the same thing. We can consider the factorizations of all of the three numbers and then find their common multiples by the same idea. Right? So first, can anyone factor the three numbers? Or say, can anyone tell me the prime factorizations?
Andrew?
Yes, Andrew, go ahead.
It's 2 squared, 2 cubed times 3 for 24.
Good.
And then 36 is 2 squared times 3 squared.
Oh, very good. How about the last one?
And then 42 is 7 times 2 times 3.
Good. So actually it's recommended to write it as 2 times 3 times 7. Right? So we usually list from the smallest power to the largest power. Well, so you can see that in the prime factorization of the LCM, so there must be a power of 2, power of 3, and power of 7. Right? Because power of 2 is in all of the three factorizations, and power of 3 is in all of them, and the power of 7 is in the last one. So what will be the power of 2?
2.
Good, so that's 2 cubed. How about the power of 3?
Squared.
It's squared, very good. How about 7?
It's just 7.
Just 7, very good. Well, so this is the prime factorization of the LCM. So eventually you just need to multiply them together. So I guess that's 7 times 8 times 9. And well, if you have time, you can just multiply them together to figure out the answer. All right, so any questions so far?
No.
Great. So this is the standard process to find LCM. I think in the next 2 questions, they are the same things pretty well. Let's go through them very quickly. So let's look at 330. So our LCM of 1,600 and 2 times LCM of 500 and 300 is equal. So we can check that they are equal. Right? And let A and B be 2 integers. Must we have LCM of 2A, 2B equals 2 times LCM of, oh, sorry, that should be A and B. All right, so sorry about the typos. So the question is, if LCM of 2A and 2B equal to 2 times LCM of A and B. So the answer is yes. So in this case, you can still consider the prime factorization of the 2 numbers, right? So like 2A is equal to 2 times the prime factorization of A, right? And the 2B equals 2 times the prime factorization of B. So in this case, you can see that in the prime factorization of LCM, so there must be additional 2, right? Because it must contain both of the prime factorizations of 2 and 2b. So basically, that will be 2 times. So you see the rest of them. From the rest of them, you can find the least common multiple of A and B. Right. So that's why there is additional factor 2 on the right hand side. So we can see that it's also true if you multiply both of the 2 numbers by 15. Right? So it doesn't change anything. Right? And for the question D, so you actually can see that. So for both of them, there is a common factor 1, 0, 1, 0, 1, 0. And 7 times 1, 0, 1, 0, and 1, 0. So you can use the property above. So let me list the property there. So AX, AY equals A times LCM X and Y. So that's the property. So here, A, X, Y are arbitrary positive integers. So in this case, you can just consider X as 6, A as 1, 0, 1, 0, 1, 0, and Y as 7. So that's why this is equal to 1, 0, 1, 0, 1, 0 times the LCM of 6 and 7. So that's still 1, 0, 1, 0, and 1, 0, right? Because 6 and 7 they do not have any common factor, or say the only common factor of 6 and 7 is 1. All right, so 31. So this is pretty long problem. So a church rings its bells every 15 minutes. The school rings its bells every 20 minutes, and the daycare center rings its bells every 25 minutes. So if they all ring their bells at noon on the same day, so at what time will they next all ring their bells together? Actually, so the first step is to extract the like, or say the mathematical.
Who's host?
I can't hear him.
Yeah, same.
Whoa.
Just kind of black.
I think somebody's gonna be. Who came here first? Is he frozen? Aiden Z is the host now.
Noise.
Oh. He came back.
All right, so sorry about that. Well, my computer was down. Can you hear me this time?
Yes, I can hear you.
Oh, great. Thank you. All right.
We can't see.
Can you see now?
Yeah.
Oh, great. So, all right. So this question is about. So basically, this is still a question about the least common multiple. So basically, we like to find. So consider the scenario. So we know that they all ring the bell at 12, right? And so basically, you know that the next time the church rings bell will be 12:15, then 12:30, then 12:45, and so on. So the next time the school will ring the bell will be 12:20, 12:40, 1 p.m. and so on. So the next time the daycare center will ring the bell will be 12:25, 12:50. The next time it will be 1:15 and so on. So basically we're looking for the least common multiples of the three like gaps, right? The 3 times. And then then you just add that time to 12, then that will be the next time they all ring the bells together. Right, so basically we're looking for the LCM of 15, 20, and 25. So this is pretty easy because we know that 15 equals 3 times 5, and 20 equals 2 squared times 5, and 25 equals 5 times 5, so which is 5 squared. So their least common multiple will be 3 will be 2 squared times 3 times 5 squared. So, well, so eventually you can calculate the answer, which is 300. So actually, the 300 here is the minutes, right? So you see that the unit here is minutes. So that means after 300 minutes, they will ring the bells together. So 300 minutes is 5 hours. So the next time they will ring the bells together will be 5 p.m. Right. All right, so any questions so far? So if you want to calculate it by using the hours directly, that also works. But before that, you have to transform everything, like all of the minutes into the hours, like 1/4, and so 20 minutes is 1/3, and 25 minutes is like 5/12. So because this involves the fractions, so it's not recommended to write it to do it in this way, right? So it's still recommended to calculate it by using the minutes and then transform it into the hours. All right, so let's look at the next one, 32. So there is a number. So the number 16 and 128 is a multiple of 7, 6, and 8. So what is the smallest multiple of 7, 6, and 8 that is greater than 16, 122? Well, so in this case, so you can see that, so we can still find the LCM of 6, 7, and 8 this time, right? And then, but there is an additional requirement. So this number must be greater than 16, 128. So that means you're looking for a multiple of their LCM, and that number is greater than 16, 128. Right. So this will be the first step, right? So find the LCM, and then you can consider the prime factorization of 16, 128. So let's see what is that. So let's do it step by step. So that's 8. Then 4032. So so it's still divisible by 2. All right, so this is how we find the prime factorization by using the short division. So you can see there are 1, 2, 3, 4, 5, 6, 7, 8. So that's equal to 2 to the 8th times 3 squared times 7. So let's see, what do we need to make the LCM of the 3 numbers? So that will be 2 cubed times 3 times 7. Right. So you can see that this number is much greater than this. And you can see that their division is 2 to the 5th times 3. So that's the quotient between 16128 and the LCM. So basically, if you're looking for the smallest multiple of the LCM, which is greater than that number, you can just add 1 here. You can just add 1, then that will be the next multiple of the LCM, and that is greater than the number 16128. Right? So that will be 1 plus 2 to the 5th times 3 times the LCM of the 3 numbers. So that's the answer. Right. All right, so let's look at the last one. So what is the smallest positive integer greater than 1 that leaves the remainder of 1 when divided by 6, 7, and 8? So even though it looks different from what we did previously, right? So in the previous questions, all of those numbers are multiples of something, but in this case, it's not, because there's a remainder. However, if you don't consider that number, so instead of considering A, so we can consider A minus 1, right? Because if you divide all of the 3 numbers and have the remainder 1, so that means if you subtract the number A by 1, then that will be a multiple of the LCM. So that means A minus 1 is divisible by the LCM of 6, 7, and 8, right? Because it's divisible by all of the 3 numbers. That's equivalent to say it's divisible by the LCM of the 3 numbers. Well, so we have found that in the previous question, right? So that's basically that's 8 times 21, so that's 168. So in this case, the smallest number A will be, so that means A minus 1 is a multiple of 168, then the smallest A will be 169. Then let's look at the question B. So for the smallest positive integer number that leaves the remainder of 5 when divided by 6, a remainder of 6 when divided by 7, and the remainder of 7 when divided by 8. Well, so even though in this case, so for when you divide all of the 3 numbers, they have different remainders, but if you add 1, then it must be a multiple of 6, 7, and 8. Right? So if you add 1 and it's divisible by 6, that means if you divided A by 6, you have a remainder of 5. If you add 1 and it's a multiple of 7, so that means if you divide A by 7, you have a remainder 6. If A plus 1 is a multiple of 8, then that means if you divide A by 8, then you have a remainder 7. So basically, in this case, we consider the number A plus 1. And again, by the argument above, you know that A is 167, right? Because we are looking for the smallest A. All right, so any questions so far? So usually, in the number theory problems, if a number is not a multiple of another number, or say if you know the remainder, usually we'll transform that into what we know. Like you can subtract the remainder and then that will be a multiple of another number. Or if you add something, or if you add like a certain number, then that will be a multiple of a number. Then you can use the techniques we learned to solve that. So that's the basic strategies to consider this kind of questions. All right, so let's start the next section. So in the next section, actually, even though it introduces another concept which is called divisor, but it's nothing different as what we learned, right? So basically, so A is a multiple of B of B. So that's equivalent to say B is a divisor of A. Right? So basically they are equivalent. Well, so here, so definitely you have to assume that A is a non-zero integer, right? So basically, a zero cannot be a divisor. Right, so find all positive divisors of 64. So I think sometimes it's also called factors. So I believe they are the same thing. So can anyone find all positive divisors of 84? So again, here you can consider the prime factorization. Or you can just consider the divisors directly. Right? So you can start trying from 1 to 84. So let me do that because there are a lot of. So the first one will be 1, then 2. So actually you can find them pair by pairs. Right? So once you know that 1 is a divisor of 84, then you know that 84 is another divisor of 84, right? Because 84 over 1 is 84. Then once you know that 2 is a divisor of 84, then you know that 42 is another divisor of 84. Then 3. So if you do that by 3, then that will be 28. So because 3 times 28 is 84. Then 4, 21. 5 is not. 6 does. So 6 is. So if you divide 18 by 6, then that will be 14. Then 7 is 7 a divisor of 84? Yes.
Yes.
Good. So 7
Yeah.
is another divisor of 84. Then the next one will be 12. So 8 is not. Right? So 9 is not. 10 is not. 11 is not. So we can stop there, right? Because when you try the next one, 12, you'll see that it is a divisor of 84, but the next one, the other one you find will be 7. And you have found that, right? So basically, this is why, actually we mentioned this right, at the beginning of the chapter 3. So we only need to test the number between 1 and the square root of that number, right? So basically, in this case, the square root of 84 is greater than 9. So, but less than 10. So basically, you can stop here. So after checking 10, if you know that it's not a divisor of 84, then you can stop. Right? So this is why you stop, because if you continue to check that, so basically you just revert, even though you can find more, but basically just revert what you have found. Right. So this will be the answer. Then count the positive divisors of each integer from 8 to 18. Oh, so by the way, so I'm sorry, just one more minute for the for 34. So you can see that in this case there are 12 divisors. So my question is, do you have a general method to find the number of divisors of a given number? So is there a method to find the number of divisors? Definitely, we only consider the positive divisors. Of a given number. So the hint is to consider the prime factorization. So for example, if you know that the prime factorization of 84 is, let me see, it's 2 squared times 3 times 7. All right, so if you know that the prime factorization of 84 is 2 squared times 3 times 7, then how can you obtain the number 12? So without listing anything. So when the number is small, definitely you can do what we did in 34. So what if there is a 5-digit number? What if there is a 10-digit number? So it's not possible to list all of them, or say it's possible, but it takes time to do that. So if you have the prime factorization, so please think about, is there any way to figure out the total number of the divisors of the given number? All right, so this is a question. So if you're interested in this topic, we can talk about it next time. All right. So count the positive integers. Well, 30. Yep. So from 18 to 8, from 8 to 18. So which of these integers have odd number of positive divisors? So again, let's think about it. So which of these integers have an odd number of positive divisors? Yeah, that's great. So that's the answer, perfect square. So why is it? So we can go back to what we did for 84. So you can see that usually the divisors appear in pairs. So, I mean, if 1 is a divisor, then 84 is another divisor because their product is 84, right? So they are a pair. So if 2 is a divisor, then 42 is another divisor because their product is equal to 84. So they are a pair. So if there are odd numbers of positive divisors, so that means, so there's a number times itself equals something. So that means that number must be a perfect square. Well, so that's the answer, perfect square. Very good. B, so there is one integer. Oh, well, so we haven't answered the question A. So is there any perfect square between 8 and 18?
Yes.
So what is it? Or what are they?
4, 9, 16.
Between 8 and 18.
Oh yeah, 9 and 16.
Good, so they are 9 and 16. All right, so B. So there is one integer between 20 and 30 that has an odd number of positive divisors. Which one? So which one is it? It's a perfect square and it's between 25 and 30. So what is it? 25, right? Good. So which positive integer have an odd number of positive divisors? So basically, they are perfect squares. All right, so the next one, 36. Note that 20 is a divisor of 60. So must every divisor of 20 also be a divisor of 60? Please do not write anything on the board. Genova, please stop writing. Thank you. All right, so let me go through them very quickly. So the first one is yes. So every divisor of 20 must be a divisor of 60. So you can check that. I mean, you can try any divisor of 20. And actually, yep. So you can also consider the prime factorization. Must every divisor of 60 also be a divisor of 20? No. So for example, 30. Right? So 30 is a divisor of 60, but it's not a divisor of 20. Well, because even though this fact is pretty simple, but it's very helpful when you, so when you think about some questions. So 37, so suppose that 3 is a divisor of k, and 3 a divisor of k plus 3, so yes. So again, actually we did pretty similar examples at the beginning of the chapter 3, right? So you can still write k as 3m or 3 times something, right? Then everything can go through. Then b, so if suppose 3 is a divisor of both of b and c, must 3 be a divisor of b plus c? Yes, right? Just by the same process. So suppose that, so in this case, you can write b as 3m and c as 3n. So suppose that 3 is a divisor of b plus c. Must 3 be a divisor of both of b and c? No. So for example, b is 1, c is 2. So their sum is a multiple of 3. It doesn't imply both of them are multiples of 3. Well, so after introducing the concept divisor, then we will talk about the next one. It's called greatest common divisor. So again, so this is designed for 2 or more numbers. Okay? So it's easy to check if a number is a divisor of a single number. Right? So what if a number is a common divisor of 2 or more numbers? Okay? So that's called common divisor. So in this case, it's denoted by GCD bracket. So sometimes they use parentheses. So that's the same. So it's just called GCD. Well, so let's look at the question 3.38. So list the positive divisors of 18. So basically, that's pretty easy. Right? So they are 1, 2, 3, 4 is not, 5 is not, 6, then 9, then 18. Okay. So you can just do what we did in 3.34, right? So you can do that pair by pair. And then, so for 24, so you have 1, 2, 3, 4. 5 is not. 6, 8, 12, 24. Right? So you can see that for 24, there are 6. So there are 8 divisors. Then can you find all of the common divisors, all of the positive common divisors? So again, we just want to see if there is anything in both of the lists. So 1 is, so 2 is, 3 is, 6 is. So that's it. Then what is the greatest common divisor of the two numbers? So basically, we just need to find the largest one. Right? So that will be 6. Right? Because 6 is the largest one. All right, so any questions so far? So actually, this is a question to see the existence of such a number. Right? So no matter what the two numbers are, so you can always find some common divisors. At least one is always a common divisor of A and B. So for any A and B. Right. So no matter what the two integers are, so 1 is always a common divisor. Right? So that means such a number, GCD always exists. Right? So the worst situation will be 1. Right? So sometimes it could be larger. So for example, in this case, that's 6. So for example, if you consider the GCD of 2 and 3, right? So both of them are prime numbers. So you can see that it's 1 because only 1 is the common divisor of both of the two numbers. So if you list the divisors of 2, so they are 1 and 2. If you list the divisors of 3, so they are 1 and 3. So you see 1 is the only common divisor. All right. So actually you can, so later we will generalize this conclusion here. So first let's look at 39. So find the prime factorization of each of the positive divisor of 24. And well, so this is parallel to what we did in the previous section for the least common multiples. So here you can see that so 24 equals 2 cubed times 3. So you see any divisor, so 1 is nothing to say, right? So 1 is just equal to 1. It doesn't have a prime factorization. So 2 is a prime number. 3 is a prime number. 4 equals 2 squared. So 6 equals 2 times 3. 8 equals 2 cubed. Then 12 equals 2 squared times 3. Then 24 equals 2 cubed times 3. So you can see that for all of those divisors, so their prime factorizations are part of the prime factorization of 24. That makes sense, right? Because this is what we got in the previous section. So you see 2 is a part of 2 cubed. 3 is a part of 3. 2 squared is a part of 2 cubed. So 2 times 3 is a part of 2 cubed times 3. So 2 cubed is a part of 2 cubed. 2 squared times 3 is a part of 2 cubed times 3. And 24 is 24 itself. So actually this is a very, again, it's an important idea to find the GCD, right? So actually this is the, so the method of finding GCD is based on this observation. So the prime factorization of 1944 is given. So we want to know if those numbers are divisors of 1944. So here we just need to check the same thing, right? Is this prime factorization a part of the prime factorization of 1944? Right? So clearly 108, yes, but 45 is not, because 5 is not a part of 2 cubed times 3 to the 5th. Right? How about 48? Is 48 a divisor of 1944? So we just compare the two factorizations. Is 48 a part of, is a divisor of 1944? In another word, is 1944 a multiple of 48? It's not, right? Because 2 to the 4th is not contained by 2 cubed, right? So that's why, so 48 is not a divisor of 1944. All right, so how can we find the GCD of the two numbers? So again, so the first step is to list the two prime factorizations. So in this case, the two numbers are 360 and 48. So let's write them down. So 360 equals 2 cubed times 3 squared times 5. Right? So basically that's 36 times 10. And 48, we have it. So that's 2 to the 4th times 3. Then how to find the prime factorization of GCD?
It's basically like the LCM, where you like look at the same base, so then 2 to the 4th and 2 cubed. So then you just find out like the smallest. So just say 3 by second to the second power, and then there's also another 3. So you just do 3 times something, not 3 to the second power. So there's 2 to the third power, so you use that, and then 3, and then 5.
So is there 5? So is 5
no, there isn't 5. No, there isn't 5, because you only do like common.
Yes, great. So the keyword is the common here, right? So any factor in GCD must be in both of the prime factorizations. So this is in both prime factorizations. Or say in all of the prime factorizations. So if there are more 3 or more numbers. So basically, because we're looking for the greatest one, so that's why we want to pick the exponents to be as large as possible, right? So definitely, if you do 2 squared times 3, it's still a common divisor of 360 and 48. So this is a common divisor. But it's not the greatest one. Right, because we are looking for the greatest common divisor, right? So that's why we want to pick the exponents to be as large as possible. So basically, this is the greatest common factor of the two numbers. So so you just pick them from the prime factorizations. Well, so we can do the same thing for in 3.42. Right? So you can see no matter for the LCM or GCD, we always need to find the prime factorizations of the two numbers. So let me summarize here. So for both of them, you always need to find the two prime factorizations. Right? So for LCM, you need to find the one that contains both of them, contains all of the elements in both of the factorizations. But in GCD, you just need to find the greatest common part. Well, so let's just do them one by one. So let me do it because we only have 10 minutes left. So for 27 and 39, so 27 equals 3 cubed, and 39 is 3 times 13. So you can see that the common part is only 3, right? Or say 3 to the first. So the GCD will be 3. So for the second one, so 100 is 2 squared times 5 squared. And the 63 is 3 squared times 7. So you see that they don't have any common factor in the prime factorizations. So in this case, so GCD is equal to 1. Right? So you see, they are all of them are different. Right? So in this case, the prime factorizations is equal to 1. Then let's look at the third one. So because the two factorizations are given, so we just pick the common part. So both of them have the powers of 5. So the common part will be 5 squared. And both of them have the powers of 11. So that we just multiply 11. So that's the GCD of those two numbers. Well, so if there are 3 numbers, it's nothing different. So 72 equals, say, 2 cubed times 3 squared. Then 240 equals 2 to the 4th times 3 times 5. Then 288. So what is that? I think that should be 64 times 9. So that's 2 to the 6 times 3 squared. So again, to find the LCD, we just need to find the common part of all of the 3 factorizations. So you see all of them have the powers of 2. So the common part will be 2 cubed. And all of them have the power of 3. So the common part is 3 to the first. And only the second one have the power of 5. So it's not in the GCD. So basically this will be the GCD of the 3 numbers, which is 24. All right, so for 43, so it's pretty parallel to what we did in the previous section. Please stop rotating your camera. All right, so actually for 43, so you can do the same thing. Or you can think about this question by the same idea. So you can still consider the prime factorizations. And then let me leave 44 as a homework. So in this case, because it's asking what is the smallest possible number of backs. So if you want the number of bags to be as small as possible, that means you want the number of candies in a single bag to be as large as possible. So if you say, well, so every bag has only one candy, that's possible, right? But it's not the largest one. So that's why in this case, we're looking for the GCD of 70 and 42, right? Why is it? Because it says every bag has the same number of candies. So every bag of candy in this store has the same number of candies, right? So that means the number of candies in a single bag must be a divisor of both of 70 and 42. And so that's why we're looking for the greatest common divisor of the two numbers. Well, so it's important to talk about the remark 1. So like what we discussed, so sometimes the common divisor of the two numbers is equal to 1, because in that case, there's nothing common in their prime factorizations. So in this case, the integers are called relatively prime. Right? They may not be prime numbers, but they can be relatively prime. So for example, 4 and 9. So if you consider the GCD of 4 and 9, so it's 1 because 4 is 2 squared and the 9 is 3 squared, right? So they don't have any common term in their prime factorizations. So they are called relatively prime numbers. So they are relatively prime. However, neither of them are prime numbers, right? So both of them are constant numbers. So that's why please distinguish the concept of relatively prime with the prime numbers. So they are not the same thing. However, if the two numbers are prime numbers, they must be relatively prime. Right? So like if you consider the GCD of say 19 and 23, right? So they must be relatively prime because, so you see, for the prime numbers, they only have two divisors, 1 and itself, right? So that's the definition of prime numbers. So definitely their selves cannot be a common divisor, right? So only 1 can be a common divisor. So their GCD must be 1, right? So that means the two concepts are different, but one of them implies the other one. Right? So if the two numbers are prime numbers, they must be relatively prime. And in this case, so if we go back to the question 3.45, then there is a very interesting conclusion. Right? So if A and B are relatively prime, so then you can easily find the GCD and LCM of the two numbers. Then GCD of AB is just equal to the product of the two numbers. Right? So you don't need to do anything, you just need to multiply them together. And in this case, their LCM, oh, sorry about that. GCD is a common divisor. So that means their common divisor is equal to 1, right? So that's the definition. But their LCM will be easy to calculate which is the product of the two numbers. Well, so this is also easy to understand because there's nothing common in their prime factorizations. So to contain both of them, you just need to multiply them together. Right? Well, so I think 46 is an application of both. Right? So you just apply that to see 46. All right, so this is the class today. And I want to remind you guys that we have the first midterm exam next week. So basically the exam will be posted tomorrow and you guys have 1 week to complete the exam. So I think there are 15 problems, and for the first 7 problems, there are multiple questions. Like for each one of them, there are 2 or 3 questions. And everyone is supposed to complete the exam by yourself, right, without any help. And I think, I mean, most of the questions are from the homework problems. And even though they are pretty similar, but it's still not recommended to like one, like you just put your homework here and copy. So it's not useful at all. Right? So it's useful to evaluate how much you learn in this class, right? So it's recommended to everyone is supposed to complete it by yourself and without any help. All right, so and see you next time and good luck to your exam. Right, bye-bye.
Bye. Thank you.
Yeah, you're welcome. Bye-bye.
Bye, thanks.
Mm-hmm.